Welcome back. So, in today's video lecture, we will try to look at the concepts of surface axis, right, and Gibbs dividing plane, and we will also look at the different types of surface axis and their consequences, right, and for example, positive surface axis, negative surface axis. We will try to you know uh, uh, talk about what is the uh, implications of the Gibbs dividing plane. Okay, and we will see after that we will see the we'll try to solve one problem in tutorial. Okay, let's begin. Right. So when we talk about surface axis, surface axis is often denoted using Greek letter, that is gamma. Okay, gamma. So when we say surface axis, you can also alternatively call it as uh, you know uh, surface concentration, right? Surface concentration, which is nothing but n by a, right? Which is different from the concentration that we usually refer to, that is n by v. Okay, so here what is this n? N refer to the number of atoms or molecules at the interface, and a, this is nothing but interfacial area. Okay, right. Now we will look at basically what is uh, meant by the positive surface. There are two types of surface axis. One is the positive surface axis, and the other one is negative surface axis. Okay, we look at the implications of these surface axis, right? Let's first understand what is the positive surface axis. Let's say you have got a beaker, okay, and you want to add some solute molecule like surfactant. Okay, so as soon as we add the surfactant into the medium, what will happen is the surfactant has got a tendency to go to the interface and absorb at the interface, like something like this. I'm sorry. So let's say they'll go to the interface and absorb at the interface, right? Okay. So what will happen is, as a function of concentration, let's say if I have to measure the some interfacial property, let's say some surface tension, as a function of concentration, you will get the slope which is negative slope, right? The slope which is negative. Okay, because as a function of concentration, surface tension decreases in this case, because the surfactant has got a tendency to go to the interface. As soon as they reach and absorb at the interface, they will reduce the surface tension, right? Now we our equation, that is nothing but the surface axis, which we will see in the next lecture when we derive the Gibbs absorption isotherm. This equation is basically function of the d gamma by dc, uh, multiplied by, I think there will be some other term, right, which we will see when we derive the Gibbs absorption isotherm, but this equation will have negative sign. Okay, so when you plug in this value which is negative slope into this equation, you would get the surface axis which is positive ultimately. Okay, so this is nothing but positive surface axis. Okay, but in some other case, like for example, when we deal with the inorganic solute like NaCl, right, NaCl mixture. So here the tendency, it will be different behavior. One would observe a different behavior, which means that if I measure the surface tension, which is gamma, as a function of concentration, right, I would see the surface tension to go up. right, increases as a function of time. Say for example, if you take reference gamma as 72 millinewton per meter, right. So, surface tension when you stuff the water with the NaCl salt, you will see that the surface tension slightly increasing as a function of concentration, right. So, why is this behavior observed, right. So, in this case the surface tension increases as a function of concentration because this is a positive slope, okay. When you plug in this value into the equation, you will get a negative value ultimately. So, which is nothing but negative surface excess. Okay. So, you might wonder why this is happening, right. So, first of all, when you add NaCl, the chlorine atom especially will have a greater affinity towards the hydrogen atom. So, what will happen is this NaCl molecule in the bulk will create some sort of a cascading effect with the water molecule, which means that there will be water molecule in the vicinity of the interface, right. There will be water molecule in the vicinity of interface because of the affinity between chlorine and the hydrogen atom. So, this molecule will be pulled towards the uh, NaCl in the bulk, right, further. So, as a result of which one can expect the increase in the surface tension, right. So, as we stuff more NaCl salt into the equation, this will actually attract, right, more water molecules in the vicinity of the surface. So, you will see that because these water molecules are now pulled towards the NaCl, it creates some sort of a cascading effect, okay, or crowding effect, right. So, that will actually cause increase in the surface tension as a function of concentration. So, that is why this uh, you know solute molecule will lead to the negative surface excess, right. Right. So, now we have seen the positive and negative surface excess. Now, what is the consequence of this, right? So, the consequence of this is, uh, let us say we are dealing with, let us say we are talking about immiscible mixture. We have one phase that is hexane and we have another phase that is water. This you can call it as alpha phase, and the water, the subphase you can call it as the beta phase. Let us say I am now adding some x amount of, okay, surfactant type A and adding y amount of surfactant type B. Now, you might wonder what is going to be my uh, total number of the surfactants that are present in the solution. So, that is nothing but x plus y, right. But this is actually this is our expectation, right. So, intuitively our intuition will say that this is additive, right, but it is not the case. So, when you measure with the actual number of moles will be slightly uh, you know uh, lesser than the expected number of mole. It is because some surfactant molecule present in the bulk, okay, they have greater tendency to go to the interface and absorb. When they get absorbed, some amount of the surfactant molecule go to the interface and absorb. So, some of them are not available for the measurement, right. So, since some of them have gone to the interface, when you make the measurement in the bulk, they will not be available for the measurement. So, which will lead to change in the number of mole that uh, one expect, right, one that we usually expect, right. It violates the conservation of mass in this case, right. It's because they got a tendency to go to the interface. These surfactant molecules will not be available. So, this is one consequence, right. Similar way you can also understand negative consequence when you measure the uh, surfactant molecules in the bulk when you talk about the negative surface excess, right. Right. Now what we will do is we'll understand something about the interface, right, more in detail. Let's say we perform some measurement using some probe, right, and we use this probe to move across the interface and try to understand or measure the property in the both the paces, right, from both the paces, right, faces. So now let's say I have the container in which I got two phase, one is alpha phase, another one is beta phase. Now I'm going to introduce some sort of a probe, right? I'm going to introduce some sort of a probe. This will measure some property in the bulk and adjoining phases, right? So if I do that, I understand that. So let's say I measure some property, some average property, right, as a function of distance, right, as a function of distance across the interface. So you expect that the property in the bulk, because let's say we are measuring surface tension in the property in the bulk, it will have some constant value, right. In the similar way, this is alpha phase. Similar way in the uh, bulk, which is beta phase, it will have the value same in the throughout the bulk, right, because you understand that there will be the alpha phase is a homogeneous phase, beta is itself a homogeneous phase, right, separately or individually. So when you measure the property will be same throughout this phase, property will be same throughout this phase, but in between these two phase, near the interface, there will be a fluctuation, okay, because the distribution of the number molecules or atoms in the vicinity of the near the interface will drastically differ, right. In such case, you would expect change in the profile. It can be sometime linear, it can be exponential, or it can be any profile, right. So maybe for brevity you can understand that it is linear. So in this case you can say for sure that the property near the interface changes drastically, right. But so based on this measurement, so let's say this distance that is covered by this probe is the tau, right, tau, okay. Now if you want to understand what constitutes the interface and where exactly this interface lies, for example, whether the interface lies somewhere here, somewhere here, somewhere here, because we know that near the interface the values are changing, but where exactly this interface, this that thin layer exists, right, lies, that we don't know. It is very difficult to locate that, right. So for that, what we Gibbs had proposed is that there is something called dividing plane, okay. There is something called dividing plane. So Gibbs uses this dividing plane, to as a reference plane. Say for example, you have the you know so something, if you choose a plane, this is nothing but a reference plane. In this reference plane, my surface axis is 0. So if you choose a reference plane such that your surface axis is 0, then you can relate this reference plane is as the interface, right. So remember, when you look at the interfacial boundary, although it appears one can visualize the interfacial boundary through naked eye, but in actual sense, the thickness of the interfacial zone or boundary is few nanometer in dimension, right. Sometime Armstrong or sometime nanometer in dimension. So so since it is very thin layer, right, mathematically we can refer to that plane as a plane in which the volume doesn't exist, right? Mathematically, the volume doesn't exist. So, V is equal to 0 in that case. It's a very thin plane. So, mathematically, there is no such boundary, but although it exists, right? It exists in reality, right? So, one can refer that plane as a reference plane with volume. It occupies no volume, right? So, this is the Gibbs dividing plane. It is also called reference plane. So, this you can locate, name it as x naught. So, x naught is the distance, right? X naught is the reference plane, okay, right. So, what is the advantage of this? Say for example, whenever you deal with, let us say, a binary mixture, okay, whenever you deal with the binary mixture, usually one would have solvent, okay, and the surfactant, okay, solvent and the surfactant, okay, all right. So, so if you choose the dividing plane for solvent, usually solvent molecule do not have any tendency to absorb at the interface, right. So, usually the solvent will exhibit a profile in a very symmetrical way, okay. Usually the solvent will exhibit a profile in a very symmetric way because they do not have any tendency to absorb at the interface. So, in this case you can choose the uh, this surface axis such that when you divide this into 2 of, okay, when you divide this into 2 of, uh, exactly at this point the gamma equal to 0, right, because uh, this is this side and this side, when you measured there will be equal number of surface x's, right. So, you can say that at this point my x is the interface exists. So, at this point my interface exists. So, I can say that surface x's is 0. Now, when you say surface x's is 0 at this point, uh, so there is only only one component left, that is surface excess of the solute molecule, right. Surface excess of the solute molecule, that is surfactant in this case. So, it is easier for us when you have the equation for surface excess, especially for binary. One of the surface excess component we can denote, I mean we can neglect, because we choose the dividing plane such that uh, the surface axis is 0, okay, right. It will be more clear when we show the presentation, so that you will understand better, right. So, the idea of this dividing plane is one cannot easily locate the interfacial point. So, so to do that, one has to choose the reference plane such that uh, you can achieve, I mean you can make the you can divide the distribution, the profile, the distribution into two equal of, so that the midpoint is exactly where the interface lies, right. So, you can say that that is nothing but your dividing plane. Okay. So, idea is to use that reference plane to say that the surface excess for solvent molecule is 0, right, that is the idea. Okay. So, now if you know that, now we know the V is nothing but you have V alpha plus V beta, right, and V sigma. There is another thing that exists because there is also interface, but mathematically this V sigma is 0. So, we can say that this dividing plane help us to uh, cancel this V sigma, right, because mathematically it has got no volume. So, you can use this relation to calculate what is known as the surface excess for given solute. So, Ni, so if I refer, if I denote this Ni alpha as the number of ith species, right, at the interface, which is nothing but so when I do that, we have to do the component balance here. So you will have Ni total, okay, minus you will have Ni alpha minus Ni beta, right? Right. So now if I convert this Ni total, so this will be Ni total as such minus Ni alpha, I can write it as a Ci alpha into V alpha minus Ci beta into V beta, okay. Now I can just now modify this. Now Ci alpha, so V alpha I can rewrite as V minus V beta minus Ci beta into V beta. So if you rewrite this, you can write this as Ni total, V beta is common, then I can say Ci alpha minus Ci beta, okay, and minus I also have Ci alpha into V, right. So this is Ni alpha. So if I divide both the side by area, which is interfacial area, I would get Ni alpha by A is nothing but Ni total V beta Ci alpha minus Ci beta minus Ci alpha V divided by A, right. So we can you can now understand, note that this Ni alpha by, I am sorry, Ni alpha, it is not Ni alpha, it is Ni sigma, it is interface, right. Yeah, this is interface. Okay, so alpha and beta are two adjoining bulk phases. Sigma refers to interface. So Ni sigma by A is nothing but your gamma, right? Gamma I. This is nothing but your surface excess. All right. Yeah, it will be more clear when we look at the presentation that we have. This is nothing but the surface excess, right? So you can see the profile of the surface excess for solvent. This is for solvent molecule. This is for solute molecule. Okay. For solid molecule, because surfactant has got adsorbing tendency, there will be one I mean, it is not always possible that you expect symmetrical distribution or symmetrical profile, whereas in the case of solvent, because they do not have any adsorbing tendency, you will expect a symmetrical distribution, right. So this will make us to identify, right, a midpoint such that the uh, the surface axis, left and right, both the side, when you sum up, they will be this side it is all negative, this side it is all positive. So both will be equal to 0, right. Whereas in this case, because they are asymmetrical in nature, the distribution is asymmetrical in nature, you will not be able to get equal of. So solute here will be very difficult to identify what is the midpoint or what is the reference plane, right. But here it is very easy to understand the reference plane, because at this point you got a midpoint where the gamma here the excess gamma excess is 0, right. So when you identify the midpoint, it is easy for us to calculate the or to say that. So whenever you deal with the binary mixture, let us say, it is easy for us to ignore one of the components. Let us say for solvent, you can ignore easily, to say that by saying that when you at this midpoint or at this dividing, when you use this as a dividing plane, at this point the surface excess for solvent is 0. Based on that, you can calculate the surface excess for the solute, right. So that is the idea, right. This is all about the Gibbs dividing plane. Now let us say we are talking about surface excess and positive and negative surface excess and equilibrium, right, surface excess. Okay. So what is the direction of the transport of the solute molecules is something that we need to understand. If you look at the adsorption surface negative, if the number of molecules, right, the molecules at the interface, if the concentration of a surface excess of the molecule at the interface is less than the equilibrium surface tension, then you would expect the monomer transport, the direction of the monomer transport will occur from the bulk to the interface. The direction of the movement of the molecule will be from the bulk to interface until they attain equilibrium, right. At the equilibrium, because they have already reached the equilibrium, there will be no net movement between bulk and interface in this case, right. Whereas in the case of the positive surface excess, if the surface excess is more than the equilibrium, in that case, because it is a positive surface excess, so you will have more number of atoms than the equilibrium concentration. You would expect that there will be a desorption, right. You can expect that there will be desorption. So monomer will usually travel from the diffuse from the interface to the bulk, right. So these are uh, based on the equilibrium surface excess concept, right. Yeah. Now you can see what is the consequence of the surface, the dividing plane. If we choose different dividing plane, how the surface axis is changing, right. The nature of surface axis is changing. If you see that exactly when you choose a dividing plane such as that, you found a midpoint, and at this point reference plane gamma is 0, right. In this case the gamma, I mean this gamma is 0, whereas here if you choose the reference plane slightly towards the right, closer to the the adjoining bulk phase, you would expect that the surface excess will be less than 0 in this case. Okay, you would expect negative surface excess in this case. If you choose the dividing plane little farther from the from the midpoint towards left, you would expect the surface excess, positive surface excess in this case. So so this will lead to some setback, right, because we are not able to identify a proper we are not able to choose the reference plane in appropriate way, right. Now we will see a tutorial based on the CMC, critical micellar concentration, which we have seen in previous lecture, right. Uh, when we try to derive the change in Gibbs free energy for micelle. So when we derived the change in Gibbs free energy of micellization, we know that this equation exists, right. So this equation we saw, we derived when we dealt with the micellization, right. So in this equation, you know what is to be known is the critical micellar concentration, that is CMC, right. For the case of CTAP, that is the CTAP surfactant, the concentration CMC of that is given 1 millimolar in water, that is already given. The temperature data is given. Okay. So they have given also the change in enthalpy of micellization at standard reference state. So what is being asked is calculate the delta G micellization at standard reference state and entropy, change in entropy of micellization at standard reference state. That is this we need to evaluate these two unknown, right. So we know that if you want to calculate the Gibbs free energy of micellization at standard reference state, this is the formula. Because we use the this is in since we use this capital G here, you can assume that n here is 1, right. So it's supposed to be nRT, you can assume n to be 1 in this case, right. So we know that so whenever you evaluate the CMC, you have to evaluate with respect to some standard reference state. In this case it is a pure water. Okay, you can assume, you can take this value as such, considering that the standard reference state is a pure water. right, which is 55.5 moles per liter. So, when you substitute this, you would get the value for delta G micellization at constant reference standard reference state will be minus 27.065 kilojoule per mole, right? Right. Now, when you substitute this into this equation, because delta H micelle is also given, so in this case your delta S micellization will be approximately 100 joule per mole Kelvin. Okay, right. So, in this way you can calculate what is the change in Gibbs free energy of micellization at standard reference state, and delta, since in this problem delta H is given, you can also calculate change in entropy of micellization at standard reference state. We will stop here.